Hi guys, I hope you all are doing good. Anyway, today we're going to start off with Bayesian method advantages and disadvantages. So what are the advantages that you can think of a Bayesian method? Well, technically it is based on a sound mathematical concept called probability. So we are not leaving it to some kind of guesswork. So we can surely say that to some extent our expectations are proper when we use Bayesian method. Now coming to disadvantages, the biggest one that I can figure out here is the need for space. Now why do I say that? Let us assume that we have a case where we have four events A, B, C, D. Now these can be hypotheses, events, or evidences in any order. And if I want to find out the probability of A given B, C, D dash, now how would I do that? Now if we use the relationship between conditional probability and joint probability, this as you see is conditional probability. So I can rewrite this as ABCD dash divided by probability of BCD dash. So this is according to the relationship between conditional and joint probability. And how do we find this? So probability of ABCD dash, you're supposed to be looking for true values for ABC and a false value for F. So pretty much this thing, the last but one row. So that would give you the probability of ABCD dash. And the probability of BCD dash, you can obtain it in several places because you just have three variables here. So there could be more than one entries here. You're supposed to be adding up all those probabilities. So let us try finding them out. Yeah, this one right here. I'm not sure if it is highlighted, but this is a row I'm talking about. 1, 2, 3, 4, 5, 6, 7. Seventh row from the top. So that would be added. And which other ones can be added? Alright, I found another one. Last but one. So these two probabilities need to be added in order to get probability of BCD dash. Now the problem is this is not the only question that can occur. I can ask you various other things. So in order to totally represent this system, I need to find out this combination of 16 values. Now that's a lot. If I have more events occurring, then I would have to increase the number of values here, find out more probabilities. Now that is cumbersome. In reality, these events here, they are not always independent. As I told you that if there is a hypothesis, there is a evidence associated with it. Obviously they are related. So Bayesian belief networks, the first concept that we are going to look at, which is like an advancement to your Bayesian method, it makes use of those links between the different events that are occurring. So Bayesian belief network is pretty much an acyclic directed graph. So you have nodes. So this is one of your Bayesian belief networks. So here you have nodes, and then you have links associated with these nodes. So these nodes, they represent your different events, and the links here, they represent the dependencies between these events. So this is a case that is similar to your previous 4 event case, except that these events are interdependent, which is more realistic in nature. As you can see here, all the nodes are of different nature. For example, these nodes A and B, they're sort of like independent. They need not depend on any of the other probabilities. The reason being, they do not have any parents. So these are called as independent or unconditional nodes. If you look at C and D here, now C has a parent and D has a parent. If the probability of A changes, then the probability of C will definitely change. Similarly, the case is with D because it is dependent on both A and B. And the nodes of this nature, which have parents, they are called as conditional nodes. And since the C and D, they do not have children, they're also called as hypothesis nodes. So please make sure that you are aware of these. Anyway, so the main reason why I'm looking at this thing is because this time around, I do not have to store 16 values to totally define the system. Why is that so? Now, since my A and B are independent nodes, they don't depend on any other node. It's enough that I know probability of A and probability of B. I do not have to find out joint probabilities. because they're not dependent on others. Now, if you look at C here is only dependent on A. So in order to totally understand what C does, I have to find out the probability that C occurs when A is happening and the probability that C occurs when A is not happening. So that is the reason in order to define C, these two are enough. And let us look at D now. Now D is only dependent on A and B. It is not dependent on C. So in order to totally define D, I need to know when D occurs, when both A and B occur. So that is this thing. And when D occurs when A is occurring and not B is occurring. And when D occurs when A is not occurring and B is occurring. And when D occurs when both A and B are not occurring. So instead of storing 16 values to totally define the system, now I can answer pretty much any question on this system by just using these 8 values. So that is the reason Bayesian belief networks are much better than your naive Bayesian methods. So what do I mean by it being better? Now look at this thing on the screen. Now this is how you would usually represent your P of A, B, C, D. Yeah, so you write P of A, B, C, D as this thing. Now how did this thing even come about? You can look at the small screen right here, small part. Now that explains why it is so. So you basically use the relationship between joint probability and conditional probability. You get this first step, and from that you expand this further on, you get this thing. Then you expand that further, you finally get this thing. So that is like your general expression for joint probability of ABCD. Now that is in the Bayesian method. In the Bayesian belief networks, from the example that we have just seen, instead of writing all of this, we just write this. Why? Because D is only dependent on AB, C is only dependent on A, so this C of AB now becomes only C of A because it is not dependent on B. Similarly, B is independent, so it doesn't depend on A anymore. So we write this down as P of B. Similarly, we have P of A here, and I've associated a few properties with each of these. Now this is an example from your textbook. So in case you have already read it, that's fine. If you have not understood it, this is the time to do it. Anyway, so let's say I give you a question. I want to find out the value of P of A given C. Now if you guys remember, A was independent whereas C is dependent on A. So from the relationship between joint probability and conditional probability, we can write P of A given C as P of AC divided by P of C. Now P of AC is joint probability of both C and A. So I can rewrite P of AC as P of C given A into P of A. So P of C given A is already present in the question. Now this is P of C given A. So I'm saying that A is already present, and then I have to find out the probability that C exists. So that is this thing, 0.4. Similarly, I have P of A, which is 0.3. So I can find out the numerator directly. The problem is with the denominator. In order to find out P of C, you have to find out all these probabilities. Now, although it looks pretty big, it's pretty much sufficient. Like all this information is pretty much sufficient in order to find out all this information. So it is not as scary as it looks. There's another advantage with whatever we have just computed. The reason being, P of AC here, the joint probability of both A and C being present, can be expressed as something like this. So AC with BD, AC with B dash D dash, AC with B dash D, and AC with BD dash. So these are already components which are present here. They're all represented with dashes. So we have already computed half the answer, which is 0.12. We just have to compute the values for A dash BCD, A dash B dash CD, A dash B dash CD dash, and A dash B CD dash. So how do we go about doing that? Now look at this part. This is the way we are going to find out A dash B CD. So just by using our formula of joint probability, we write down this as P of D A dash B because this time around we have an A dash instead of A, and we know that D only depends on A and B. So this is just like this formula. Looks just like this, except that you respect your complements here. And this is multiplied with C given A, P of B. This is also supposed to be A dash and into P of A dash. So this would give you some number. Similarly, A dash, B dash, C, D. Same thing over here. You respect your complements. So that is the reason you're not writing A. Instead, you're writing A dash and B dash. Similarly, you find out the value here. Similarly, you find out the value for this one. Similarly, you find out the value for this one. You add up all these four values with 0.12. So it will become 0.12 divided by 0.12 plus whatever is the sum of these four values. So that is pretty much how you compute the values in the case of Bayesian belief networks. Now I want you guys to do another problem, a much easier problem but a more realistic problem. So that would be your third question in your assignment number 2. The third question for the assignment is on your screen. So as you can see, we're looking at a scenario where rain, sprinkler, grass wet are your different events, and rain is an event that is sort of like independent. And that is the reason you just have two probabilities T and F associated with it. Sprinkler is dependent on rain. Grass wet is dependent on both sprinkler and rain, and that is the reason you have four combinations here, whereas sprinkler just has two combinations. So what I want you guys to do is use the concept of Bayesian belief networks and then find out the probability that it would rain if you have wet grass. Cheers. For this question, I recommend you guys do not use this formula right here, that is the Bayes theorem, because it would totally make your answer go wrong. The reason being, grass wet is not an individual event as was in the case previously. So it isn't just wholly dependent on rain. So you cannot use this probability straight away. So instead of doing this, do the one which you see in green here. So this is the right way of doing it. So the probability, the joint probability of rain and grass wet should be represented by this way. So it will be represented as probability of rain, grass wet and sprinkler events happening together plus the probability of rain, grass wet and the negation of sprinkler event happening. So just like how you find out the probability of grass wet by using all the different conditional probabilities, do the same for your upper numerator as well.